This session we're going to hear from Jens's ancestors and descendants. We've got first up Peter Mosses, who was Jens's PhD dissertation advisor, talking about verification of denotational semantics of inheritance. You defined it, but you didn't verify it, right? So now, 20 some years, 30 years later, we got to verify it.
Thank you for the introduction. First of all, congratulations, of course, to Jens in this celebration of, in connection with his 60th birthday. I gather it's not quite his 60th birthday yet, but still we'll celebrate as if it was. I'm delighted to be able to contribute to the celebration today. To start with, I'd like to look back 35 years to when Jens and I were both at Aarhus. He was the first PhD student I ever supervised, and a really good start to my career as a PhD student. But supervision is not really the right word when it comes to Jens. He had no need at all for my supervision. I gave him some advice from time to time. As you see from this publication list, this is just taken from DBLP, that he didn't exactly restrict himself to his thesis topic. He started a very fruitful collaboration with Michael Schwarzbach on type inference, and those highlighted ones there are the ones that are co-authored with Michael. Unfortunately, Michael is no longer with us. With Dexter Cozen, also, he co-authored the first of his many Popple papers. It wasn't published during his PhD studies, but I'm sure it was written during his PhD studies. What I'd like to do is to look at the very first of his papers, which is this OOPSLA 1989 paper. How many people were at OOPSLA 89? Okay. Oh yeah, that's good. That's not. You may remember that it's co-authored with William Cook. Again, sadly, no longer with us. Died a few years ago. It was written when Jens was in the first year of his PhD, and so the OOPSLA was in the autumn of his start of his second year. It's also one of his most highly cited. I think it's his second most highly cited paper, with more than 500 citations on Google Scholar, which is far more than I ever had in any of my publications. When I first heard about this celebration, and somebody alerted to me the fact that Jens had got older since he was a PhD student, then of course I started looking around for an idea for a paper, well, I started at the beginning of his DBLP list, and of course this was the first paper that I looked at, and so the idea that I had, well, first of all, when I reread the paper after so many years, I was impressed by how elegant the semantic definitions were. Simple and elegant, and the proof of the equivalence between actually an operational and a denotational semantics using step index was also very elegant, and not unrelated to my own interests as well. So my initial aim with this, what is now turned into a paper in the proceedings, which you can download because it's open access, was that I would simply type in Jens's semantic definitions into a proof assistant and verify it. And I'd also wanted to experiment with an alternative form of step indexing. I won't go into the technical details of that, but I wanted to use a proof assistant because nowadays that's more or less mandatory in connection with any publication, that you don't just put an ordinary LaTeX proof in, but you put in something that's machine checked. And for various reasons, I decided to use the proof assistant Agda. How many people have used Agda in the room? Right. No, there's actually slightly more than I expected. It's a relatively new proof assistant. It's not as old as Coq. It's related to Coq. In any case, if you want to read Agda, you can read the paper. In this talk, I'm not going to be dragging you through the literate Agda specification that takes up sections 4 and 5 of the paper. In the rest of this talk, I'll first talk about denotational semantics and fixed points, because Jens's original paper and analysis of inheritance with William Cook was based on the notion of fixed point. This is also very closely related to my own start in denotational semantics. We'll look at the semantics of inheritance, which Jens gave both an operational method lookup semantics and a denotational semantics. I'll give you a little taste of how it looks in Agda. And then we'll finally look at how you prove a lemma in Agda. So let me now go back even further than to Jens's paper, go back to the work of my own supervisor, Christopher Strachey. And he wrote a paper in the proceedings of an IFIT working conference with a delightful title, Formal Language Description Languages. You can parse that any way you want. It was published in '66, but the work was done starting in '63, and it was written in '64. So that's really quite a long time ago, something like, 60 years ago? I don't know whether you'll be able to read this at the back. Can you read that at the back? Yeah, okay. So then I won't try to read it out verbatim just to save time, but just let me say that Peter Landin, I guess many people in functional programming know Peter Landin for his contributions to functional programming. He was translating Algol 60 into lambda notation, but he had an abstract machine and he had side effects in his lambda notation and a jump operator. So it wasn't a pure lambda notation. Strachey very much wanted to not have any machine in the picture, however abstract. He just wanted to have pure lambda notation because he wanted essentially to be defining pure mathematical functions. He'd become convinced that lambda notation and pure functions was the way to define the semantics of programming languages. He was, as I say, wanting to define semantics by translation to lambda notation with the intention that those lambda expressions, they would be simply defining mathematical functions. But he had a problem. He needed to use a fixed point operator. And that fixed point operator had a self-application in it, very similar to the self-reference that you get in object-oriented languages. There was no known interpretation as a function of that fixed point operator at the time that Strachey was doing it. So he was doing all this, he was wanting everything to be a pure mathematical function, but here he had an operator which actually was not. And it has the unfolding property that if you apply it to a function and do some reduction, then you get this expression here, which is where f has just been wrapped around it, and you can carry on doing that, and it unfolds. This is a fixed point. It is a value, an argument to y, such that it's an argument to f. This y of f expression, such that when you apply f to y of f, then you get y of f back. So that's a fixed point, and that was a well-known operator. Strachey was using it. Dana Scott was horrified at that because there was no known mathematical interpretation. And so he comes along with his domain theory, which was actually, first of all, he tried to prove that there could be no model, but then in the process of the proving, he actually discovered how to construct the model. This is called the D-infinity model, and it's quite a famous model of the lambda calculus based on the notion of continuous functions. And then you have a fixed point function, this fix here, for any domain D. If you apply it to a continuous function from D to D, then it gives you the least fixed point of that continuous function. It can be defined in the same way that as a so-called Kleene approximation limit. And then Scott and Strachey together, that was essentially denotational semantics in the early 70s. And I was fortunate enough to be in Oxford at the time as a student of Strachey and also to have access to Dana Scott, and it was a very formative part of my development. So now back to Jens. So we've got fixed points sorted, and Jens, I don't recall exactly how much Jens was working with denotational semantics. He was working actually with action semantics quite a lot, which was a hybrid of denotational and operational semantics. But it seems he really liked this denotational semantics. I'm going to show you some snippets from his paper. So hold your hats. He abstracted, together with William Cook, they abstracted from the concepts of object-oriented languages to method systems, which was a very simple thing that still had inheritance in it, but didn't have any of all the nasty features like imperative variables and lots of other things. So they had this part with the syntax of the message systems with these very, very simple expressions. This one here is calling a method M in what they call an instance, or you think of it as an object given by the value of E1 and passing it the argument E2. Jens, I guess you remember this quite well. Maybe everybody else is going to have to take it on trust. Note also there were some extra operations with a class hierarchy that was assumed to be finite and where the root had no methods. Note in particular this parent operation here that takes a class and tries to give you the parent, but of course if it's the root already then there is no parent, and so think of this question mark here as a kind of maybe type that it might or might not give you a class. And here you see that it's used to give a case analysis between two different expressions. The square bracket notation is case analysis. So this will be significant in a moment. There are also some semantic domains around. One of the nice things about denotational semantics is you can just define your domains recursively without any regard to positivity or contravariance. And in particular, these domains are nastily recursive in that this domain of fun includes functions from values to values, and those values could be behaviors, and behaviors could essentially include functions again. So there is a real cycle in the definitions of these, but that's fine in denotational semantics. We know from the work of Scott and Strachey, or rather Scott I should say, that such domain equations, they have least solutions up to isomorphism, and you don't even bother to mention the isomorphisms. So now let's look at this is the method lookup semantics with three mutually recursive functions, send, lookup, and do. I'm not going to take you through all the details, we don't have time for that, but at this point I really have to, in a rather embarrassing way, quote the acknowledgement at the end of this paper from '89. The authors would like to thank me for helpful comments on the second part of the paper. That should imply that this was entirely accurate and bug-free, this semantics, right? Now, this is the embarrassing bit. So remember that parent is something that might give a class back, so it's a maybe type as a result. Here it's used as an argument to lookup, which takes a class, not a maybe class. Now you could say that, well, okay, in this case it's guarded by root, it tests whether it's root, and so here it's in a sense safe from a dynamic point of view, but here there's no guard, okay? So this was not something that I noticed when I reread this semantic definition. It's not something that I ever noticed when I originally read it, but it is something that Agda noticed when I fed it into a proof assistant. And that's not the only thing here. Remember that an expression can evaluate to a behavior or a number. Now, I'm not really quite sure what Jens expected to happen when you called a number with a method and an argument. This M is a method name, essentially, and this is the argument. But if this is not a behavior, it's not expecting to be sent a message. Again, that was something that Agda did. The third thing is actually very trivial, this double use of F here, which Agda also complained about, but was actually fixed in the journal version of this paper. The other two were not fixed in the journal version of the paper. So the referees of the paper, the reviewers, also had the same blind spots that I had. So a bit embarrassing for me personally. By the way, I should say that I didn't go out expecting to find any bugs in Jens's semantics. I was wanting to just verify that they were perfect. Now, this is the denotational semantics, and because Jens had proved it equivalent, then indeed you expected to have exactly the same issues. So to be really disconcerting if it didn't. Now I'm going to give you a brief taste of what it looks like in Agda. So just to recap very quickly, Agda is a purely functional programming language with dependent types. If you don't know dependent types, then read the paper a bit and hopefully you get the idea. It's also a proof assistant based on the Curry-Howard correspondence, which says that essentially a proof is a program, and the formula it proves is the type of the program. Again, please just accept that that's a fact of life. So now let's see how it looks with this semantic definition. We're going to introduce a concept of domains. These are all assumptions of this module that you can write in Agda. Agda doesn't really care whether you can discharge these assumptions, and in fact the idea that you could take a fixed point of any arbitrary function here from the carrier set of this is a carrier of the domain, the set of elements of the domain, that you could take an arbitrary function here and find its least fixed point is just an unrealistic assumption, but that doesn't stop you using Agda to check the definitions. So here's some more Agda. This is just the way that we're going to deal with classes without this parent operator around. We're using a data type here, an algebraic data type with essentially having an origin class and subclasses of that. So you automatically get a finite hierarchy. When we define domains, then we're going to use isomorphisms here, and that introduces implicitly in Agda with these funny curly brackets, introduces overloaded functions to and from between the left and right hand sides of a domain definition. And finally, you have the syntax of the language more or less as in the paper, just a bit simplified here to fit in the paper properly. So here's the definition in Agda of what you'd seen previously in the denotational semantics copied from Jens's paper. It looks a little bit messy with all these froms and tos, which are the isomorphisms, which you never bother to mention normally in denotational semantics. So let's get rid of those. And it looks a bit, if you squint now, then it really looks pretty much like Jens's original definition, except for this case, which is now much more complex. Remember that it's possible that this first expression could be evaluated to a number. So we're going to cover that case explicitly, and also it might not implement that method. So we also want to deal with that case as well. Okay, so now towards verification. Just very briefly, the idea was to have an approximate semantics based on the notion of fuel, an extra argument, a natural number that you fed as an extra argument, and then you just counted down. The only place it counts down is actually from here, I think, with self from n to n minus 1. Everywhere else it's just copied over. And this is for n greater than 0 that you have these equations. Then there's a lemma that I'll illustrate how one case looks in Agda. This is the whole proof in the paper of that lemma, just by structural induction on the syntax. This is how the statement of the lemma looks in Agda. And again, there's this issue with the parent occurring there. Yep. And by using this child here, which essentially says that here we're dealing with a class that has a superclass, then we avoid that difficulty there. And then the actual the particular case for self, this is the way it looks in Agda, and again you can relate it very closely to the way it looked in the original. I'm running out of time, so I'm going to conclude now. So you can find many more details in the paper and in the other material. But before I get to the real conclusion, I'd like to give a little birthday present to Jens. So this is the book in which Christopher Strachey's paper appeared. This actually is not just any old copy of this book. This is Christopher Strachey's own copy of the book, which I inherited when he died in 1975. So even if you already have the book, then you don't obviously have that particular copy. As I say, this is not available online, and so now, Jens, you have something I hope you will take good care of and pass on to your own descendants. So let me conclude really now what I've done, and it drew attention to some issues with the difficulty of taking a denotational semantics and pushing it into Agda and verifying it. Not due to it was good that it found a few inconsistencies, but actually it was quite painful to get to that stage. And what I'd like to do in the future, if I get the chance, is to make it easier in Agda to just put in a denotational semantics without all that extra fuss with making these isomorphisms explicit and things like that. So thank you for your attention.
Thank you. We do have time for one or two questions. John, you can come up and get started. I do want to say also that if anyone else can find bugs in 35-plus-year-old papers of Jens's, that would be a great thing for the rest of the... but if you do, you also have to give him a really nice gift. So
many thanks for this book. This is like precious. So this is my academic grandfather, and a very famous one at that. I want to say one more thing. This proof that Peter talks about, actually the idea came from him in a way. I went to him and I said, we're trying to prove this, what do we do? And he pointed to a paper by Peter and Gordon Plotkin on limiting completeness, which is a difficult proof about something also with denotational semantics and so on. And I read that, and I think I got the idea. And what I learned today is that in a way that was very early step indexing. But so in many ways, maybe that paper was the very beginning of step indexing, which is now used everywhere.
The one that was published and got all the 500 citations, my paper with Plotkin has about 7.
But anyway, I think many lesser men would have said, look, I'm your PhD advisor, I gave you the idea for how to get to the proof. He would have said, I want to be a co-author. And he never did that. So this is like the most generous person I've ever met. He never asked to be a co-author of anything I was working on. And he just helped me and advised me, and it was wonderful.
Thank you.